Dear all, good morning. Our last unit. In this unit, first lecture is Jordan canonical form. Now, in this lecture, we are going to discuss how to write a Jordan canonical form for a given matrix. In the last class, we discussed diagonalization. We know every matrix, every n by n matrix is not diagonalizable. Is not diagonalizable. Yeah, the Jordan canonical form give more general similarity transformation. Give more general similarity transformation. Diagonalization is the diagonal matrix is similar to diagonal matrix. We discuss this one. That means AP equal to PD or A equal to PD P inverse. This one we discussed last class. Now here give the Jordan canonical form give more general similarity transformation. Now we'll see what is that. Before going to Jordan canonical form, what is the Jordan block? The Jordan block JK lambda is the eigenvalue. K by K matrix with lambda on the main diagonal. This lambda is on main diagonal and 1 on the super diagonal. That means above the main diagonal elements. Suppose it's a 1 by 1 Jordan block. That is only one eigenvalue. But 2 by 2 Jordan block. Lambda not it's a main diagonal. That 1 is the super diagonal. It's a 3 by 3 matrix. Lambda naught is the main diagonal. 1 is the super. Suppose 4 by 4 Jordan block, like the main diagonal is lambda naught, lambda naught, lambda naught, and lambda naught. 4 times 4 by 4 matrix. That is super diagonal is 1 0 0. Next 1 0 1 0, like it's a 0 0 0 0 0 0, like this one. Super diagonal elements are 1 1. So, now in general, by K matrix. K by K only main diagonal elements are that eigenvalue, super diagonal elements are all are 1 1. Above the super diagonal and below the diagonals are all are zeros. This is the Jordan block. This is the Jordan block notice. Now note, suppose a Jordan block has only one eigenvalue, lambda equal to lambda naught. That lambda eigenvalue, the algebraic multiplicity is K. Means that is determinant of JK equal JK minus lambda naught. This is lambda naught. That's lambda minus lambda naught or K is the algebraic multiplicity. Lambda naught is eigenvalue. Algebraic multiplicity is K. K times repeating. Now geometric multiplicity is 1. Suppose J naught is 2 times repeat. It means algebraic multiplicity is 2. Geometric multiplicity must be 1. In that case, Jordan block is just now we saw. Main diagonal element 0 0. This one. Super diagonal is 1. Now, yeah, this generalized E1, E2, Ek denote the standard basis in dimensional vector space. Then Jk lambda not equal to E1. Jk means this one. Yeah, this one. Or we can take suppose 2 by 2 matrix. Okay, we'll go for suppose 2 by 2 matrix. Suppose we are taking this one. Lambda not 1 0 1 by 2 lambda naught suppose equal to lambda j to lambda e1. E1 means in that dimensional vector space 1 0. The same as you can write, if multiply this one, you get lambda naught only. Lambda naught 0 0. That means lambda naught 0. That is same as the lambda naught into e1. Similarly, if suppose if e2 suppose lambda naught 1 0 lambda naught e2. G2 is this e1. J2 lambda naught e2. This is 0 1. This equal we are getting 0 1 0 lambda naught. That means we are getting This one get lambda naught uh, E2 plus E1. Or the same as that one, lambda naught, this one carrot 0 1 plus 1 0. That one is the notation. Suppose kth dimensional vector space. In that case, you get JDK lambda naught E1 equal lambda naught E1. At ith one, lambda naught, the combination we get lambda naught EI plus EI space vector. This one correct. Like that one. We are writing U2. It is combination of that lambda naught U2 plus previous one E1. This is the one. Now, Jordan canonical form. What the definition? A Jordan canonical form is a black diagonal n by n matrix. Black diagonal, Jordan black diagonal n by n matrix. See now J is equal to JK lambda naught 0, 0. These are all are 0 black diagonal. These are the diagonals, Jordan blacks. Now with J Jordan blacks, JK lambda 1, JK lambda. That means lambda 1 eigenvalue with K1 by K1 Jordan black, K2 by K2 Jordan black with lambda 2 eigenvalue. So each one is the Jordan black. This also denotes a zero matrix. Zero denotes a matrix. Matrix. Suppose we are getting eigenvalues are 2, 3. Okay. This algebraic multiplicity is 2 and this algebraic multiplicity is also 4. That means total we get 4 by 4 matrix. In that 4 by 4 matrix, we get 2 by 2 Jordan block with eigenvalue 2, 2 by 2 Jordan block. So if we take this algebraic multiplicity is 3. 2 by 3 Jordan block with like this one 2, 0, 1 for diagonal 0, 2. This is 1 block. Next, we'll get again this eigenvalues main eigenvalues are in the main diagonals. 3, 3, algebraic 3. It is repeating 3 times. That means super diagonal 1, 1, this is 0. Like this one. These are total zeros. Zero matrices. Like this one. 1, 2, 3, 5. Okay, 2 plus 3, 5 by 5 matrix. Like this one. And only main diagonal, this were the Jordan blocks. Corresponding with eigenvalue. Lambda 1 eigenvalue. This is another Jordan block with lambda 2 eigenvalue. And so on like this. Now the sum of this orders. The 2 by 2 order. This is 3 by 3 order. Sum of all order equal to the total matrix order. K1, K2, K. This all of order is equal to n. Each submatrix, this is Jordan block is the some submatrix. Each matrix order is equal to total matrix. This is Jordan canonical form. Properties of Jordan canonical form. Determinant of Jordan J minus lambda. This is equal to lambda minus lambda 1 whole for K1 and so on. Lambda 1, lambda 2, lambda are eigenvalues. The K1, K2, K are its multiplicity. Lambda 1 algebraic multiplicity is K1, lambda 2 algebraic multiplicity is K2 and so on. Now the Jordan canonical form has n eigenvectors. Corresponding each eigenvalue will get eigenvalue, eigenvector. Lambda 1, lambda 2, lambda eigenvalues. Corresponding each eigenvalue, we are getting each eigenvector. x1, x2, xn. So now each one multiplicity, geometric multiplicity is 1. That one. Okay, that means we are writing corresponding Jordan block. That means geometric multiplicity is 1. Every n by n matrix A is similar to Jordan canonical form. A is equal to S, J, S inverse, where S is the matrix. This S is contained in the diagonalization. A is equal to we are writing P, J, P, PD, P inverse. Here P is contained the eigenvectors. Eigenvectors of A. Here also S is the matrix contain the eigenvectors and generalized eigenvectors of A. If we P contain total eigenvectors, suppose A is n by n matrix, this P is contain n by n eigenvectors. But corresponding A, this is not diagonalizable. If it's n by n eigenvectors, it's diagonalizable. Suppose the matrix A has n by n matrix, it has n eigenvectors, and it's a diagonalizable. Suppose it's not has n eigenvectors, less than n eigenvectors, that means it's not diagonalizable. In that case, it's a special case, Jordan canonical form. In this Jordan canonical form, this matrix S has contain the eigenvectors and generalized eigenvectors. Now see what is the generalized eigenvectors. The definition: if A is an n by n matrix, a generalized eigenvector of A corresponding to the eigenvalue of lambda is a non-zero vector x satisfying a minus lambda I or k into x equal to 0 for some positive integer k, so that a minus lambda I k minus 1 x is non-zero. So what that means? A minus lambda I power k x equal to 0 means this a minus lambda I whole power k is lies in the null space or null space. That x belongs to lies in null of a minus lambda I whole power k or the null space of a minus lambda I whole power k. This is generalized eigenvector. Okay, now we'll see how to find generalized eigenvector. Okay, some example. And the generalized eigenvectors of a matrix. This one. It's a upper triangular matrix. Now we know the eigenvalues. Direct I am writing. The eigenvalues of A are lambda equal to 3 1 1. So 3 1 1. What the algebraic multiplicity of lambda equal to 3 is 1. That means corresponding lambda equal to 3 we get one eigenvector. What the algebraic multiplicity of lambda equal to 1 is, we'll see what the geometric multiplicity. So if I get geometric multiplicity is 2, this is a diagonalizable. If geometric multiplicity is 1, it's not diagonalizable. In that case, we go for canonical form. Canonical form. Now first find eigenvector corresponding to lambda equal to 3. Eigenvector corresponding to lambda equal to 3, a minus 3i x equal to 0. That implies minus 2 1 0 0 minus 2 2 0 0 1 into x1 x2 x3 equal to 0. Now on this one, one can write the this implies minus 2x1 x2 equal to 0 minus 2x2 2x3 equal to 0 and x3 equal to 0. See, x3 equal to 0 means x2 also 0. This is x2 plus 2x3. See, 1 minus 3. Okay, right. That means 2 minus 2x1 plus x2 equal to 0. x3 is 0. x3 is 0 means x2 also 0. Sorry. This is the minus 3. 0. Okay, you are not getting this one. Now solving this one that implies x2 equal to x3. Therefore, x2 equal to minus x1. x2 equal to 2x1. x2 equal to x3. This is x3 also the same. x3 equal to x2. Therefore, eigenvector you can take x1. x1 equal to 2x1 x1 is same, x2 equal to x1, x3 also 2x1. Means x1 into 1, 2, 2. Okay. This one x eigenvector. Therefore, x1 equal to 1, 2, 2 is eigenvector corresponding to lambda equal to 3. Now go for eigenvector corresponding to lambda equal to 1. Eigenvector corresponding lambda equal to 1. Now what is the eigenvector? A minus lambda I 1. 1 into lambda x equal to 0. That implies 0 0, that is 0 1 0 0 0 2 0 0 2 x1 x2 x3 0. This implies x2 equal to 0 and x3 also 0, 0 x2. Therefore x equal to x1 0 0, x1 equal to 1, x1 into 1 0 0. Yeah, hence x2 equal to 1 0 0 is an eigenvector. Now we get one eigenvector. The similar means it's contained, we have to find generalized eigenvector. Now a generalized eigenvector some x3 generalized eigen vector will be x3 corresponding to same eigenvalue. Because it is a algebraic multiplicity. Now we get one eigenvector, linearly independent eigenvector. That means geometric multiplicity is 1. Algebraic multiplicity 2, geometric multiplicity 1. That is not diagonalizable. I mean, you can geometric multiplicity of lambda equal to 1 is 1 only. That means we get one more eigenvector. That's a generalized eigenvector. That we get this one a minus 1 into lambda 1 into I x3 whole square equal to 0. Same as we know a minus I into x3 not equal to 0. Generalized eigenvector. This implies a minus I x3 not equal to 0. Suppose we take let a minus I x3 equal to x2. Now this implies a minus I whole square x2 equal to the same as can I write a minus I 1 a minus I x3 equal to taken x2 means a minus remaining a minus I is a minus I, this is x2 equal to 0. That means a minus I x2 equal to 0. That means we have taken a minus I x2 x3 equal to x2. So now that is a minus I whole square x3 equal to 0. You can define only a minus I x3 equal to x2. Now find this one. That implies a minus I 3. A minus I means the same as a minus I 0 1 0 0 0 2 0 0 x3 means you can take x1 x2 x3 coordinates. X2 is 1 0 0. Now solve this equation. That implies x2 okay this is now multiplying this one x2 0 0 x3 0 0 x3 equal to 1 0 0. That implies x2 equal to 1 and x3 equal to 0. Now x1 is arbitrary. Now x3 equal to x1 that's arbitrary, x2 is 1, x3 is 0. It's right. That means x1 is arbitrary. You can take any value. Suppose you can take 0 or whatever. Now x2, x1 is arbitrary. Therefore, x equal to, now we can take 0 or whatever arbitrary, 0, 1, 0. Again, is generalized eigenvector. Is generalized eigenvector. Now is generalized eigenvector. This is the one. Suppose the same problem. Now these are the eigenvector. This is generalized eigenvector. It's asking to find the Jordan canonical form. Now Jordan canonical form corresponding lambda equal to 3 1. That geometric multiplicity. This geometric multiplicity also. This is 1. Now we get Jordan blocks. Corresponding lambda equal to 3 1 Jordan block. Corresponding lambda equal to 1 another Jordan block. Now what is the Jordan canonical form? Okay, I am writing here. Jordan canonical form is J equal to the diagonal elements are 1 1 0 0 0 0 0. This is the 1 is repeating. That super diagonal element is 1. You get super diagonal element is 1. Yeah, this is the Jordan canonical form 3 by 3 matrix. Now where S is the, now in this case what the S matrix? S equal to eigenvectors. You can write first eigenvector is 1 2 2. So whatever you write eigenvalue first, that corresponding eigenvector first column 1 2 2 2. Second column first eigenvector. Right, third one is generalized eigenvector 1 0 0 0 1 0. Or you can take a 0 is any number. This is, you can take x1 is arbitrary. You can take 1 2 3 whatever. X1 is not fixed when you are solving this one. Suppose I am taking x1 is 0. You can take 1 2 whatever. So yeah. Therefore A equal to Sj S inverse. It's a Jordan canonical form. Now here is the find the Jordan canonical form of the matrix. For the find the first eigenvalues. This is the second problem. The characteristic equation of A is A minus lambda is equal to 0. Now this one you get eigenvalues. You get eigenvalues lambda equal to 3 3 3. You will get this one. Algebraic multiplicity is lambda equal to 3 is 3. We'll see what is the geometric multiplicity. Now eigenvector corresponding lambda equal to 3 means A minus 3 lambda 3i x equal to 0. That implies 0 0 1 minus 1 0.5 2.5 1 minus 0.5 2.5 minus 3.5 minus 3, that's a 1.5. x1, x2, this is minus 1 point. Sorry, here 3.5, 0.5 is 0. Now, adding R2 and R3, we get 0, 0, 1, minus 1.5, 2.5, 0, 0, 1.5. This is x1, x2, x3 equal to 0. This implies x3 is 0. x3 is 0. When you are adding this minus x1 plus 0.5, 2.5 x3, x3 is 0, then that is 0. Okay, this implies minus x1 plus 5 by 10, that's a 1 by 2, x equal to 0. Or x equal to x1. Yeah, therefore, x equal to x1, x equal to 2x1, x3 is 0. So x1 into 1, 2, 0. Hence, you take x1, this x1 is 1, 2, 0, is an eigenvector corresponding to lambda equal to 3 of one vector. That means geometric multiplicity is lambda equal to 3 is 1. Now find the generalized vector. We find the general vectors. We find the generalized vectors. Now first one, generalized eigenvector x x2 corresponding to same eigenvalue. Okay, no need to write corresponding x2 such that a minus 3i whole square x equal to 0. But it's same as if and only if we know this a minus 3i x2 equal to x1. Now solving this one, we get x2 equal to this one, x2 equal to 1, 1, 1. Now this is the x2 equal to 1, 1, 1. Now it's a 3 by 3 matrix. We require one more generalized vector. Now second generalized vector x3 such that a minus 3i whole square x3 equal to 0. If and only a minus 3i x3 equal to x2. Solving this one, now we have to take previous one. Solving this equation, we get x3 equal to 1 minus 1, 1. So these are three eigenvectors. This is the eigenvector, this are generalized eigenvector. Therefore, Jordan canonical form, JCF equal to, yeah, that's a eigenvalue is 3. by 3 matrix. Main diagonal elements is 3. 3 super diagonal. Okay, right. 3, 3, 3. This is the one. Super diagonal elements are 1, 1. This is a 3 by 3 matrix. Now, and S equal to first eigenvector. What the first eigenvector? 1, 2, 0. Next to generalized eigenvectors. 1, 1, 1, 1 minus 1, 1. This is generalized eigenvectors. Okay. Therefore, you can write. Therefore, this is Jordan canonical form. Therefore, A equal to Sj S inverse. This is the one. You can check any doubt. A is S. If you multiply J, S and S inverse, you get A matrix. That is, A is similar to Jordan canonical form. Now, give an n-by-n matrix A in Jordan canonical form. The eigenvalues are the entiers on the main diagonal. The eigenvalues are entiers on the main diagonal. Already we know this one. Now, the characteristic polynomial lambda minus lambda 1 R1, lambda minus lambda 2 R2. That means this is an algebraic multiplicity, each one. Lambda 1, lambda 2, lambda are eigenvalues, where Ri is the number of occurrence of lambda on the main diagonal. That means algebraic multiplicity. Here algebraic multiplicity is 3, it's occurring in main diagonal 3 times. If algebraic multiplicity is more, they are occurring in the main diagonals. That means this lambda 1 occurring main diagonal is R1 times, lambda 2 occurring main diagonal is R2 times, and so on like. Now the minimal polynomial. Minimal polynomial means it's a characteristic polynomial. This is also polynomial. The degree of the characteristic minimum polynomial, yeah, degree of minimal polynomial less than or equal to degree of characteristic polynomial, and this one also it satisfying the same roots. That means the roots of the characteristic polynomial and minimum polynomial is same. And, yeah, the matrix satisfies the minimal polynomial also. When that matrix, suppose a matrix is A satisfy polynomial less than or equal to characteristic polynomial. The polynomial is called minimal polynomial. Suppose lambda minus, suppose some lambda minus lambda 1 whole power 3. Suppose A satisfies this equation. Suppose A also satisfies lambda minus lambda 1 whole square. It satisfies, it's a minimum polynomial. It not satisfy this polynomial equation. It satisfy, this is every matrix is satisfy characteristic equation. That means every characteristic polynomial is a minimal polynomial. Suppose the characteristic polynomial less than degree, second degree is also satisfy that matrix A. Then you can say this polynomial is the minimal polynomial. If it's not satisfying, then the minimal polynomial is same as the characteristic polynomial. So it satisfies lambda minus lambda 1. Then you can say it's a minimal polynomial. Suppose distinct eigenvalues. Suppose a matrix has a distinct eigenvalues. The characteristic polynomial same as the minimal polynomial. Any eigenvalues are repeated. The degree of the minimal polynomial less than or equal to degree of the characteristic polynomial. Degree of minimal polynomial, degree of the characteristic polynomial more than the degree of minimal polynomial. This is the one. Now the geometric multiplicity of lambda, in the number of lambda Jordan blocks. Suppose geometric multiplicity is 1, we get only one Jordan block. Geometric multiplicity of the one particular eigenvalue. Suppose lambda 1 geometric multiplicity is 1, we get only one Jordan block. Geometric multiplicity of lambda 1 is 2, we get 2 Jordan blocks. Geometric multiplicity is 3, we get 3 Jordan blocks. Now over here, this here we are getting only one geometric multiplicity of 3 is 1. That way we will get only one Jordan block. Geometric multiplicity is 2, we get 2 Jordan blocks. We will see that one. See example. 6 by 6 matrix. Having characteristic polynomial is this one, lambda minus 3 whole power 4, lambda minus 2 whole square, and minimal polynomial is this one. And another minimal polynomial, the Jordan canonical form of A. Now you have to write Jordan canonical form. Now observe here the statements. So it's a minimum polynomial S1, S2. This power is S1. The algebraic multiplier of the minimum polynomial is S1, corresponding lambda 1, where Si is the size of the largest Jordan block. If S1 is there, the largest Jordan block, corresponding to lambda 1. At lambda 1, suppose we are getting a characteristic polynomial lambda minus 2 cube, and minimum this is a characteristic polynomial. Suppose minimum polynomial lambda minus 2 equal to means largest Jordan block size is 2 by 2 only, not 3 by 3. But total main diagonal this 2 occurs in 3 times. The where Ra is the number of occurrence of lambda on the main diagonal. Occurrence in the main diagonal 3 times. Largest Jordan block is the 2 by 2 matrix. Now we'll see this example. Minimum first one, MA lambda is equal to lambda minus 3 whole cube, lambda minus 2 whole square. Now the total main, this is the 4 characteristic polynomial corresponding to lambda equal to 3, the algebraic multiplicity. Okay, algebraic multiplicity of lambda equal to 3 is 4. Okay. And algebraic multiplicity of lambda equal to 3 is, that means it's a the lambda equal to its occurrence in main diagonal is 4 times. Lambda equal to is occurrence in 2 times. But the minimum polynomial, that means it gives largest size of the Jordan block. That means this 4 you can write 3 plus 1 is same as 2, because in the main diagonal it occurs 2 times. The largest Jordan block also 2 times. 2. Okay, that means we can write Jordan canonical form of is, means how many, the total matrix is 4 plus 2, 6 by 6 matrix. That's all. That is 6 by 6 matrix. See, now first we will get the 4 times. The largest Jordan block is 3 by 3 matrix. 3 by 3 matrix. 3 by 3. That's a 3, 3, 3. In the super diagonal we get 1, 0, 1, 0, 0, 0. Again, rotate. This is Jordan block. Next, we write another Jordan block 1. Yeah, we are getting main diagonal. Next, another Jordan block is by 2. Yeah, that means 2, 0, 2. Super diagonal is 1. This is the one corresponding to this minimum polynomial. All are zeros. This one 0, this is 0, 0. This all are zeros. Zero matrices. Now we'll see second one. What the second one is? The minimum polynomial lambda minus 3 whole square, lambda minus 2 whole square. Now this one, yeah, main diagonal elements total is characteristic polynomial 4. This 4 we can write largest diagonal elements, largest Jordan block. 4 we can write 2 plus 2. One way. Another way, this 2. Another way we can write 2 plus this 2 we can write 1 plus 1 again. We can write 1 plus 1. Now this 2 largest one in the characteristic polynomial also 2. This is same as the 2. That means we get different type of Jordan canonical form. The first one is 2 plus 2. That means we get 2, 1, 0, 2. It's 1. Another one is again 2, 1, 0, 2. Okay, this diagonal. It's occurring 4 times. 1, 1, 1, 2, 3, 4 times. This is the one. Next, Jordan block is 2, 1, 0, 2. This one. All are zeros. 0. And corresponding this one and R. Okay, R. or what we get? 2, 3, 1, 0, 3. This is one Jordan block. Next, 1 by 1 Jordan blocks. This is 3. Again, 3. Next, 2 by 2. 2, 1, 0, 2. This is the one. Okay, these all are 0. This is zeros, zeros, 0. All are zeros. Zero matrix. This is the canonical form. Okay, thank you. I'm stop here.